Hello everyone. The title of this video is Dividing Complex Numbers. Now each example I'm going to be doing in this video is taken directly from a free online calculator, an online textbook at openstax.org, and it's the Algebra and Trigonometry text. I'm in section 2.4 titled Complex Numbers, and I'm working under the objective heading Dividing Complex Numbers. So each example will be either an example from the reading or one of the try it problems from the reading or from some of the exercises at the end of the section that are related to this particular objective. I would ask that every time I bring up a new question that you pause the video and try to work on it yourself first, before watching me do it and then comparing, because you should be practicing these problems on your own as well. Alright, so all these examples were asked to divide and simplify. Alright, so to divide divide by complex numbers, and we want to get our final result in the standard form for a complex number, which was that real number plus imaginary number, right? A plus bi. Well, we have to remember one thing. Recall that multiplying complex conjugates results in a real number only with no imaginary part, with a zero imaginary part. So if you remember that, if you take a plus bi and multiply it by a minus bi, right, remember these are called complex conjugates. The result, if you FOIL, right, distribute the a and then distribute the bi, and remember that I squared is real, right? I squared is -1. It's not imaginary. You'd end up with a squared plus b squared. Okay? A strictly real number, right, with no imaginary part to it whatsoever. Right? So if you remember this, that is going to be very helpful when we're asked to divide complex numbers. And let me show you how. So off to the side here, I'll just do it in general. So I have a complex number, a plus bi, and then I divide it by another complex number, c plus di. And here's what you're going to do. We would like to set it up so that I is not in the denominator anymore. Remember, I is the square root of -1. So what we're going to be doing pretty much is just rationalizing the denominator, or realizing the denominator, making it into a real number only. In order to do this, you're going to take the numerator and denominator, right, the dividend and divisor, and you're going to multiply by the conjugate of the denominator, or the conjugate of the divisor. So if the denominator is c plus di, and you want to make it real, multiply it by its conjugate, c minus di. So we're going to multiply by the conjugate of the divisor, or the denominator. And if and you can't just multiply the denominator by something, you also must multiply the numerator by that same expression, right? You can't just multiply the denominator by something and not the numerator, right? You want to keep it equal to the original expression. Okay, now when you multiply the numerator out, right, distribute the a, you'd have, a times c, and then, minus a times di, real number here, imaginary number there. Then distribute the bi, you'd have plus, b times c times I, and then plus, plus bi times negative di, I mean minus b times d times I squared, but remember I squared is negative 1, so we end up being plus b times d, right, without the I squared. And then the denominator, right, I showed you up here, when you multiply conjugates, you get a real number only. Right? C plus di times c minus di would end up being c squared plus d squared. And then I wish to eventually write this in the standard form for a complex number. So I take the real numbers up here, right, ac plus bd, and we're going to divide that by the real number denominator, right, divided by c squared plus d squared. Right, so here's the real number part, the real part of our final result. Right, then plus, and then we have the imaginary part. So we have, the imaginary numbers up top are negative AD plus BC, so I'll make that BC minus AD. Right, negative AD plus BC, those are both have an imaginary part to it, right, have I attached. And this will also be divided by, everything up here is divided by c squared plus d squared. And this is the coefficient on I, right? So the real part plus an imaginary part, right? This is the standard form for a complex number. And this is what we end up wanting. Now that was a lot of letters. I get it. It's tough. I would not memorize this. All I would remember, all I hope you remember is that we're doing this when the denominator has an imaginary part to it. I want to realize the denominator. I want to turn the denominator into a real number with no imaginary. And to do that, we're going to multiply by its conjugate. Great. So in example 1, we have, 2 plus 5i, the dividend, right, the numerator, divided by, and then the divisor, or the denominator, is 4 minus 1i. So the first thing we're doing, right, is I'm taking the numerator and the denominator, and we're going to multiply, the numerator and denominator by the conjugate of the denominator, the conjugate of the divisor. Now 4 minus I, the conjugate would be 4 plus I. 4 minus 1i, 4 plus 1i. And I would do the same to the numerator. Right? And again, I'm hoping you remember how to multiply complex numbers. Right? I did a whole other video on multiplying complex numbers. So when you multiply the numerator, you'd have 2 times 4 is 8. And later you'd have 5i times I would be 5i squared would be negative 5. You'd have 8 and negative 5, that'd be 3 for the real number. And then the imaginary number, you'd have, 2i and 20i, so plus 22i. All right, so there's the result of multiplying those two complex numbers and simplifying. Right, I'm just kind of skipping a couple steps here. Again, I'm assuming you know how to multiply and remember that I squared is negative 1 and all that, and combine reals, combine imaginaries. And we're dividing this by, and like I said, when you multiply conjugates, you end up with, a squared plus b squared here. So 4 minus 1i times 4 plus 1i, the a and the b are 4 and 1. We end up with 4 squared plus 1 squared, or 17 in the denominator, right? So this is 3 plus 22i all divided by 17. And then to get it in that standard form for a complex number, just you're dividing each term. Now that the denominator is real, I'm going to go ahead and divide each term in the numerator by that 17. So 3/17, there's the real part of the final result in complex form, plus, and then 22/17 times I, right? So there's your real number plus your imaginary number. Right? The standard, the final result in standard form for a complex number. This is the quotient of those two complex numbers, right? The result of the division of 2 plus 5i by 4 minus I. Now, if you'd like to check this with some technology, that wouldn't be wrong, right? Now, some calculators, as I've shown you in previous videos, do have the ability of working with imaginary numbers, working with I. And I have an emulator of a TI-84 Plus here, TI-83, TI-84, very similar. And I'm in the A plus BI mode instead of real mode. That way I can actually work with the imaginary number I. And let's see what happens when I enter the original expression we had. Right, so now the numerator and denominator have multiple terms, so I'm going to put them in parentheses. So we had 2 plus 5i, right? And I is above the decimal point on this, divided by, and then the denominator, the divisor, is the quantity 4 minus I. And since I'm in this, A plus BI mode, it's going to give me my final result in that form, right? A plus BI. So this should be 3/17 plus 22/17 I. Now, at first, it's going to give me some decimals, right? And you're like, ugh, what's all that? There's the real number, the real part, 0.17647058882. Plus, and then here's the imaginary part, 1.294117647 times I. Well, if I change these should be fractions, right? It should be 3/17 and 22/17. I hit the math button, change the previous answer to a fraction, and look at that. All right, there it is, 3/17. That's 0.176470588, blah, 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 right? It actually goes on more than that. It goes on forever. Plus, and then 22/17 times I. Right, exactly what I got by hand. So, we did good work. Great. All right. So I have checked that one, and I'll just do a couple of these with the checking. All right. But after a bit, I'll leave it up to you to check the results yourself. Great. All right. The next example is very, very simple. We have, the numerator is 3 plus 4i. The denominator is a complex number. It's 2. It's 2 plus 0i. You can think of this as 3 plus 4i divided by, and then 2 plus 0i. But nobody writes this. 2 plus 0i is just 2. Adding 0 is silly. Right? It doesn't change any values. So I'm not. You can think of it that way, but I'm not going to look at it that way. All right. It's not wrong. It's just kind of meaningless. And notice that the denominator is already real. Right? It's just 2. So if the denominator is already real, we don't need the conjugate. Right? In fact, the conjugate would be 2 minus 0i, but that's just 2 again. Right? Plus 0i minus 0i. So again, if the denominator is already real, no need for the conjugate. We're pretty much done here. All I need to do now is what I did in the last example when the denominator ended up being a real number, that's 17. Just divide each term in the numerator by 2. We have 3 halves, or 1.5, plus, and then 4i divided by 2 would be 2i. And here's your final result written in the standard form for a complex number, right? You should always end up with something like this where you have a real number plus, some imaginary number, or minus an imaginary number. So the real part is 1.5, the imaginary part is 2. Right? Great. And I'll let you punch that in a calculator. That one's a very, very, very simple one. Okay. Great. All right, so the next one, see how the denominator has I in it, has an imaginary part that's not 0. So in this one, I'll use the conjugate. Right. So again, we can think of this one as -5 plus 3i in the numerator divided by, and then 2i, the real part would be 0. You can think of this as 0 plus 2i if you want. All right, there's nothing wrong with it. It's just nobody usually does this, right? Because again, adding 0 is kind of meaningless. Right? This is still just 2i. But it might be helpful here so you can actually see what the conjugate is. All right, I'm going to take this, I'm going to take the numerator, -5 plus 3i. Take this, this one-term denominator here, and we're going to multiply the numerator and denominator by the conjugate of the denominator. Now, the conjugate of 2i, right, again, if you think of 2i as 0 plus 2i, the conjugate would be 0 minus 2i, or just -2i. That's the conjugate. And then do the same thing to the numerator, right? Multiply by 0 minus 2i, or -2i. Right, now in the numerator, the real number would be 6, right? Because you have -2i, times -5 would be +10i. Right, that's the imaginary number, +10i. And then the real number, you see, -2i times 3i would be -6i squared, or +6. Right? Remember, I squared is -1. So the numerator, written in standard form, is 6 plus 10i. And 2i times -2i would be -4i squared, or just +4. All right, remember, I squared is -1. Or 0 squared plus 2 squared. Right? 0, because it's 0 plus 2i times 0 minus 2i ends up being 0 squared plus 2 squared, 0 plus 4, or 4. And now that the denominator is real, we can easily write the quotient, right, in standard form for a complex number, right, a real number plus an imaginary number. So 6 divided by 4, right, that reduces to 3 halves, right, that's 1.5, plus, and then 10i divided by 4. 10 divided by 4 is 5 halves, right? So 2.5 times I, right? And there you go. That's the final result, the quotient written in the standard form for a complex number, right? The real part is 3 halves, the imaginary part is 5 halves, or 1.5 and 2.5i, right? All right, and this one I'll do the check with the calculator, right? Because the denominator had an imaginary part that wasn't 0. So in the numerator has multiple terms, so I'll put in parentheses. We have -5 plus 3i divided by, and then now the denominator has one term but multiple factors, right? So I'm going to also put the denominator in parentheses. It was 2i. And we get, 1.5 plus 2.5i, which as fractions are 3 halves and 5 halves, right? 3 halves plus 5 halves I, exactly what I got when I did it by hand earlier. Wonderful. So yeah, so once again, if the denominator, right, if the divisor has a non-zero imaginary part, we're multiplying the numerator and denominator by the conjugate of the divisor, the conjugate of the denominator. Now, this isn't the only way I could have done this. I mean, you could have also just multiplied the numerator and denominator by I, and you would have ended up with the same result, but I'm not doing that. Okay, I'm going to stick with the conjugate stuff. Okay, great. So I got a few more of these. So example 4, we have 2 minus 3i divided by 4 plus 3i. So I'm taking the entire numerator, the entire denominator. Right, the denominator actually has a non-zero imaginary part. So we're going to multiply the numerator and denominator by the conjugate of the denominator, 4 minus 3i. Do the same up here. And once again, I'm going to kind of just say out loud the steps for multiplying. So we'd have 2 times 4 is 8. Then later we'd do negative 3i times negative 3i would be positive 9i squared, which would be minus 9. So we have 8 minus 9. The real number part of the numerator is negative 1. 8 minus 9. Then the imaginary number part, you'd have negative 6i and negative 12i for negative 18i. And so there's the numerator in standard form for a complex number, right? Negative 1 minus 18i. And then multiplying conjugates, 4 plus 3i times 4 minus 3i will end up being a real number, 4 squared plus 3 squared, which is 16 plus 9, that's 25, right? So we have negative 1 minus 18i in the numerator divided by, and now, the denominator is realized, right? It became real, no imaginary part. And then we want to put it in the standard form for a complex number, so I just divide every term up top by 25. So we get negative 1 25th plus, negative 18 25ths times I. And there you go. That's the quotient, right? The final results written in the standard form for a complex number. All right. Now, if you want, a decimal, right, this would be negative 0.04. All right, and this would be negative 0.672. Right, negative 0.72. But let's see that again. Let's check that again. All right. So my numerator here was 2 minus 3i divided by, denominator was 4 plus 3i. And see what we get. Yeah, see negative 0.04, which is negative 1 25th for the real number. And then the imaginary number, negative 0.72 times I. That's negative 18 25ths times I. If you want to see the fractions, there you go. Right. Exactly the same thing I got by doing it by hand. Wonderful. So I've checked my work. It looks good. Excellent. All right, and again, nothing's changing here. All right. So here again we have, the divisor, the denominator, has a non-zero imaginary part. So I'm going to be using the conjugate. All right, so I'm going to multiply the numerator, multiply the denominator by the conjugate of the denominator, which would be 2 plus 3i. Same to the numerator, 2 plus 3i. All right, and once again, I'll just say out loud what the steps. I'm gonna write the numerator in standard form. So you'd have 2 times 2 is 4, but then later you'd have 3i times 3i, which would be negative 9. Right, 9i squared is negative 9, so 4 minus 9 is negative 5 for the real number. Plus, and then the imaginary number would be 6i and 6i again, so 12i, Right, so there's the numerator in standard form for a complex number, negative 5 plus 12i. And then multiplying conjugates, 2 minus 3i times 2 plus 3i. This will end up being 2 squared plus 3 squared, right? 4 plus 9, or 13. So negative 5 plus 12i, all divided by 13. And now that the denominator is real, we can easily write this result, this quotient, in the standard form for a complex number. This would be negative 5/13 plus 12/13 times I, right? 12i divided by 13, or 12/13 I, same thing. And there we go. That's the resulting quotient. And this will be the last one I do this for. Let's check this, right? So we have 2 plus 3i in the numerator, the dividend, divided by, and then a divisor of 2 minus 3i. And I'll change these to fractions. Math, change to fraction. Look at that. Negative 5/13 plus 12/13 I. Exactly what I got by hand. Wonderful. Alright. Now I've got just one more of these. Now this one's a simple one. The denominator is already real. Alright. See, actually, you know what? I'll do this on the calculator as well, because I want to show you how, when I'm in that a plus bi mode on the calculator, it'll take square roots of negatives and write them as imaginaries, right? Write them with the number I. So you have to recall here, right, something I've brought up in several videos now, that if, n is a positive number, then we're going to take the square root of negative n, right, a negative number, and write it as a multiple of I, right, a real number times I. Take the square root of positive n, times I. You should always think this. You should jump to this automatically when you see the square root of a negative number, which I'm seeing here, right? So for example, right, the square root of negative 20 that you see here, I'm going to rewrite this as the square root of positive 20 times I. And again, make sure the I is not inside the square root. In fact, some people might even throw it in front. Say I times the square root of 20. Same thing, right? As long as you have those factors of the square root of 20 and I. Now the square root of 20, you know how to simplify radicals, I'm hoping, right? This is the square root of 4 times the square root of 5. So that's 2 times the square root of 5 times I, right? Or 2i, 2 times I times the square root of 5. Same thing, just with the factors in a different order. But I'll leave it like this, right? So I see the square root of negative 20. I must rewrite it this way. So we have 4 plus then 2 times the square root of 5 times I, right? That's the complex number in the numerator. The denominator is just 2. Now, you saw this with, I think, the second example in this video. See, the denominator is already just a real number, right? It's 2. 2 plus 0i, 2 minus 0i, whatever. If the denominator is already real, we can just then divide each term by that denominator. 4 divided by 2 is 2, plus, and then 2 times the square root of 5 times I, right? When I divide that by 2, the 2's would cancel, and I'm left with just the square root of 5, times I. Don't forget that the I is not in the square root. And there we go. All right. And let's check this. All right, let's check this. So I'll pull up now look at this, right? I'll put the numerator in as it is. We have 4 plus, the square root of negative 20. Right? Now, if you were in real mode, right, if you were still in the real mode, this would come back with an error. Right? The square root of negative 20 is an imaginary number, not real. But since I'm in this a plus bi mode, it'll actually come up with something. and then we're dividing this by 2. Right? And you see a crazy decimal coming up there. You know, the real number is 2, which I have, right? 2 is the real part of my final result. The imaginary part was the square root of 5, which you see they have 2.23606799777 I, right? This should be the square root of 5. Now the square root of 5 is not a rational number. It can't be written as a fraction. So if I try to change it to a fraction, it won't work. So what I'm going to do is I'm just going to check the square root of 5 and make sure it's the same number that they have in front of I here. And look at that, it is 2.236067977 times I. Right, now it goes on forever, right? This isn't the end of it. It's irrational, it goes on forever without ending, without repeating. It's just, you know, they can only, you know, it's a calculator screen. It can only go so far. So yeah, so we have 2 plus the square root of 5 times I. Exactly what I wrote down by hand. Fantastic, right? And you should always be, you know, checking your work in some way, you know, just to make sure you're doing things properly. Great. All right, and that's it. All right, so just remember when dividing complex numbers, if the divisor, you know, if the denominator has an imaginary part that's not 0, you're going to multiply the numerator and denominator by the conjugate, right? The conjugate of the denominator. That way, you'll transform the denominator into a real number, right? And once the denominator is real, then you can express the final quotient in the standard form for a complex number, right? Some real number plus some imaginary number. Great. So I'm hoping that watching me go through these 6 examples here helps you in some way whenever you're asked to divide complex numbers on your own. And thank you very much for watching.